Hello, I am Sunil Divekar with you. We'll try to solve this problem to understand the concept of stress and to learn some calculations on how to do the calculations. So the problem is determine the stress in each section of the steel bar when subjected to an axial force F of 5 kilonewton. What should be the length of each segment if the total extension allowed is 0.233 into 10 raised to minus 3 meters. Given here is a stepped bar, and since phi is mentioned, this is diameter. Phi stands for diameter, and therefore we have diameter 20 and diameter 12. The length is given as 1.2 meters, and this is subjected to a force in the direction of axis 5 kilonewton. So we first jot down the data. Let's take a look at the given data. When we talk about the given data, we have the given force here is 5 kilonewton, that is 5000 Newton. Also given is the length of that bar, so we'll call the length of that bar, the total length of the bar here as L, and that is given to be 1.2 meter. In the question also is given for this total length, the total extension allowed is 0.233 into 10 raised to minus 3. So we say that the extension, that is the change in length in this case, is 0.233 into 10 raised to minus 3 meters. In the figure are also given the diameters. Now for the sake of understanding, let's label this as 1 and this as 2, segment 1 and 2, and therefore we'll have the diameter of the segment 1, D1 here, is given as 20 mm, which works out to 0. Divided by 1000, of course, 0.02 meters. So when you divide the second diameter also by 1000 to convert it to meters, it works out to 0.012 meters. Now they are asking for the stress in each section of the steel bar. We note that the diameter here is 20 mm and the diameter is 12 mm. Unequal diameters with the same force acting on it will result in different stresses. So we try to calculate the values of the stresses. First, let's begin with the area. Since we have stress is equal to force upon area, we'll require the information on area. So for segment 1, let's call the area here A1 is pi d1 square by 4. When you substitute values, we have pi by 4 multiplied by 0.02 squared, and that gives us a value of 3.14 into 10 raised to minus 4 meters square. Similarly, for the second segment here, in this case, we have area A2, again pi d2 square by 4, and that is pi by 4 multiplied by 0.012 squared will give us an area value of 1.13 into 10 raised to minus 4 meter square. Once we have the areas, we are now good to calculate the stress. So the stress for the segment 1, this is larger cross sectional area and will have lesser stress, force divided by area, and this is smaller cross sectional area and therefore will give you a larger stress. So we have stress in this case for the segment 1 represented by sigma 1, which is force upon area A1, and that is 5000 Newton divided by 3.14 into 10 raised to minus 4 meters square, and this should give you a value of 15,915.5 Newton per meter square. Similarly, the stress in segment 2, sigma 2, will be given by force is common in this case. So we'll have 5000 Newton divided by 1.13 into 10 raised to minus 4 meters square. So this, when you calculate, works out to 44209.7 Newton per meter square. So as you can see, here we have a uniform force acting throughout the length of the bar. The diameter is larger, the cross-sectional area is bigger, and therefore we have a smaller stress value in the bigger section. However, the smaller cross-section will be highly stressed, more stressed material. Now the next part is what should be the length of each segment if the total extension allowed is 0.233 into 10 raised to minus 3, that is delta L. Now we note here that the total extension on this bar is going to be the extension of segment 1 plus extension of segment 2. So when we have this 1.2 meters taken as L, let's try to take this particular segment as X, segment 1 as X, which would mean that the remaining length will be 1.2 minus X. So in this case, this works out to L minus X, or 1.2 minus X, right? There will be a small amount of extension of this segment, so that will be delta L1. There will be fairly larger amount of extension in this smaller section, and that will be delta L2. So this will be delta L1 and this will be delta L2. The way we write it mathematically, in this case we have the total change or the total extension here represented by delta L will be a sum of the two extensions, which we can write delta L1 plus delta L2. Since this value is given, we write this as 0.233 into 10 raised to minus 3 meter is equal to delta L1, so the change in the larger cross section, plus delta L2. Let's mark this equation as equation 1. Now in order to solve this, we have to go back to a fundamental equation. I will start with this relation which says that modulus of elasticity E here, I'll write this here, modulus of elasticity is given by stress upon strain. Now this stress can be written as force divided by area, and the strain is delta L upon L, the change in length for the given length. So this we can further write it as F upon A multiplied by, when it goes up it becomes L upon delta L, or this is F L upon A delta L. In short, the basic equation here is E is equal to F L upon A delta L. Now please note that this equation is the fundamental equation in this case and has 5 parameters: modulus of elasticity, force, total length, area, cross-sectional area in that case, and a change in length. Now you can have a problem, you can receive a numerical in which any 4 of the parameters are given and you will be required to find 5th one. In this particular numerical, we are given the other parameters and we have to find out this delta L. So we rearrange in this case. Delta L here is equal to F L upon A E. Right? So this value of delta L is now substituted in equation 1. So we say substituting in equation 1. We will write in a specific manner. We'll write this as 0.233 into 10 raised to minus 3 is equal to, now what will be delta L1? Delta L1 will be F is common. We are replacing delta L1 with FL upon AE. So F is common. This will be length segment L. In our case, we have already identified this as X. So the length for the segment 1, we have already labeled it as X. So this will be upon area A1 into E plus, in this case, we'll have F. The remaining length in this case is L minus X upon area 2 into E. Please note that the modulus of elasticity here needs to be found out, and since in the problem statement it is given that steel bar is used, we refer to data book in an open book exam system. If we do not have an open book exam system, we must remember that for steel the modulus of elasticity is 200. So we have E is equal to 200 into 10 raised to 9 Newton per meter square. So it is 200 gigapascal. Coming back, we note that 0.233 into 10 raised to minus 3 is equal to, now since the force and the modulus of elasticity are common, we remove this outside the bracket. So we'll have force divided by modulus of elasticity, and into the bracket we'll have X upon A1 plus L minus X upon A2. Now when you substitute values, you will have 0.233 into 10 raised to minus 3 is equal to 5000, that is the value of force, divided by 200 into 10 raised to 9, and we have X upon the area is A1 area is 3.14 into 10 raised to minus 4 plus L we know is 1.2 minus X divided by 1.13 into 10 raised to minus 4. Now when you solve this, please note that in the entire equation X is the only unknown, and therefore when we say 0.233 into 10 raised to minus 3 multiplied by 200 into 10 raised to 9 and divided by 5000 will give you 9320 is equal to, okay, we'll have this value calculated to be 5658.8x, and therefore the value of X here is going to be, sorry, this is 12, this part I'm sorry, this is 1290 is equal to, and therefore X here is equal to 0.228. Now since we have the remaining segment length as L minus X, that will be 1.2 minus 0.228, and that works out to 0.97. So the final answer in this case here will give us L1 is equal to 0.228 meters and L2 here is 0.97 meters. That is the final answer. Thank you.